Good afternoon, everybody. My name is Mark Shellhammer. I'm the Master of Ceremonies for today's event. I direct the Human Spaceflight Lab here at Johns Hopkins University and a program we call Bioastronautics at Hopkins that aims to promote human spaceflight not only here but at other universities and institutions as well. Today's event is run by our partners Hopkins at Home, which provide video and online promotion and production. This is the eighth of these online events. First was a larger event in February of 2021. Since then, we've had five of these mini symposia on the topics of systems medicine, statistics, surgery, space radiation, persons with disabilities in space, and omics. Those are all available online. You can go to the Hopkins at Home website and track them down. Today's topic is on multi-system resilience for human spaceflight. So we'll have presentations from three people in the field. I'll call them experts, although with multi-system resilience, it's not clear that any of us are experts yet. And we'll have each one of them speak for a few words, give a short presentation, and I'll engage in a discussion with them. We'll go through all three of them, and then we'll have a group discussion, and then we'll open it for questions. You can submit written questions online during the presentations. They'll be read to the panel by Ivan Padilla, a member of my laboratory. Our timing is flexible based on discussions among our panel, but at the latest, we will end in 2 hours. That's 4 o'clock Eastern time. All right, now, excuse me, I am going to mostly read from my prepared notes because I want to make sure that I get some of the technical points correct here, or semi-technical. Today, we're going to talk about resilience, and it's a vague and general term that encompasses a variety of ideas such as robustness, self-organization, complexity, dynamic systems. We don't have a consensus even on the definition of resilience, let alone multi-system resilience, let alone multi-system resilience for spaceflight. We don't exactly know how to formulate it, how to assess and maintain it, and even if this line of thinking is necessary and useful for human spaceflight. One of the prevailing definitions, for example, is that a resilient system absorbs a perturbation or an anomaly and returns to normal function. Well, I don't like that definition. I think a truly resilient system should be able to change its goals as circumstances change, not necessarily come back to prevailing normal function. An example I often use is the collision in 1997 of a Progress resupply ship with the Mir space station. Multiple things were going wrong during that manual docking procedure, but at no time did the crew call it off and change the goal from docking now to docking eventually. There were systemic reasons for this, which contributed to the lack of resilience. Contrast that with the well-known case of the explosion of an oxygen tank on Apollo 13 in 1970. If you've seen the movie or read any one of a number of books, you may recall that there's a point where it dawns on the commander, Jim Lovell, Tom Hanks in the movie, we've just lost the moon, meaning, guys, we are not going to land on the moon. They held on to that goal as long as possible, and then they let it go. Letting it go was explicit and allowed the crew and mission control to explore new options, new ways of thinking that would be off limits if they were still trying to land on the moon. The new goal was simple survival. So, given this lack of consensus and an accepted body of practice on multi-system resilience, you might wonder what it is that we have to say today. Well, for one thing, we want to raise awareness of this as an issue. Risk mitigation alone will not suffice for something as complex as a human mission to Mars, for example, and maybe even the later missions to the moon. Just as the World Health Organization says in their charter, health is not just the absence of disease, so a resilient, well-performing spaceflight is not just due to the mitigation of known risks. There must be more, including the ability to deal with unknown occurrences, the unknown unknowns. So I will make this proposition. We can expect the unexpected in human spaceflight, and especially when we plan for missions to Mars. That's one reason we're going to the moon and Mars, to explore the unknown And that includes the unknown of how to design a mission for these extreme settings. So what do you do when you must think of everything in the design of a mission, but you know you can't think of everything? Is there a systematic way to approach this problem? What happens when known problems are mitigated? It's very much the NASA approach and not at all trivial. Well, when that happens, there's the unknowns, more specifically, unknown unknowns. Can we do this in a systematic way? It's not clear. It might be enough, or maybe the only option, to determine when a boundary is being reached in a mission, a boundary where something bad is about to happen. There are ways to do this. There are early warning signals for so-called critical transitions in dynamic and complex systems, as they're called in the literature. So maybe the thing to do is track the system for these signals, these early warnings, trust the humans in the system of systems, that is the mission, to come up with solutions when alerted and give them the resources to make the changes. That's what happened in Apollo 13, largely. So we're talking specifically here about multi-system resilience, the proper functional interaction of all the subsystems that make up a human spaceflight. A lot of my thinking on this was started when I was spending some time at the NASA Human Research Program about 10 years ago, and I was introduced to contributing factor map, which was a product of Jennifer Mindock. I believe Dr. Mindock is monitoring our conversation today. We're not talking about, to be clear, psychological resilience in and of itself, what people call grit, a form of resilience, but more the entire system of systems that makes up a complex human spaceflight. So we're expanding our domain to include things that are typically taken care of by spacecraft and mission planners and designers. So with that, let me introduce our speakers. Our first speaker, I'll introduce them in turn, but feel free, each one of them, to elaborate on their introductions and their professional backgrounds. I will say, before I turn it over to them, that all of us, me and our three speakers, are connected to professional societies of various kinds, government organizations. Some of us have spent time at NASA. The things that we're going to say today, these are our own views. They're not those of any particular government or professional society, but they should be. Okay, with that, I will turn it over to Eric Antonsen. Dr. Antonsen is associate physician at Mass General Hospital in Massachusetts, a lecturer in the Department of Aeronautics and Astronautics at MIT, Chief Technology Officer of Advancing Frontiers, a consulting company that provides spaceflight integration services. He does research on risk assessment and analysis for space medicine, artificial intelligence in medicine, the design of space health systems. He held many positions at NASA, which is where I met him. In 2022, he won the NASA Exceptional Service Medal for leadership in characterizing, evaluating, and mitigating the human system risks associated with spaceflight. He also started recently a new professional society, the Organization for Space Medicine, Engineering, and Design, OSMED, OSMED, of which the three of our speakers and me are all members. So, Eric, take it away.
Okay. Thank you very much, and it's great to be here. Just a real quick check. You can hear me okay? No problem?
Yes.
All right, excellent. So appreciate the invitation to be here, and always appreciate it when Mark tells me, Eric, you have to tell them how we have to think about everything and also acknowledge that we can't think of everything. And so you have to go set the stage for the impossible problem we're going to talk about. So since I can't solve the problem, at least I can set the stage. Multi-system resilience for human spaceflight, as you see the title here, is also the title of a paper that Mark and I and the other folks here had also worked on, and that can be found online at OSMED's website, the organization that he talked about. And with all the things that Mark put out there, one of the things that I think is really the first challenge is saying, well, human spaceflight's done okay. Why are we talking about this, right? Is there a reason to be thinking about resilience in this context when we literally just had our very first medical evacuation after 25 years on the space station, right? So we must be doing some things pretty well. And I would say that we have done reasonably well for the things that we have designed for and flown up until today. But there's a lot of things that are changing in human spaceflight, not the least of which is who's flying and where we're going and what we're doing. But also, all these systems that we're building are new today. And something like what you see on the screen, the International Space Station was really designed back in the 90s, and has been held on until today. So the systems, the software, the hardware, all these sort of things that are coming into commercial spaceflight, the next iterations of government spaceflight, the Artemis program, and eventually to Mars, are going to carry all of their own challenges. And one of the big things that it's important to kind of realize is that even when the space station was brand new, we were having major challenges that could have killed the crew if they did not have real-time support from mission control with 80 to 150 people there working the problem in real time, right? 80 to 150 people. And if you look at what you're seeing right here, this is an analysis that was put into the Safe Expeditions Beyond LEO paper done by the Ames group, Alonso Vera and his team. They looked across the 20-year life cycle of this International Space Station, and they said, let's go through all of the anomalies, all the things that went wrong, and let's just filter them out for the stuff that's high priority, and then filter them out even further for the things that really warranted ground intervention within an hour. Because when we think about our edge case, Mars, we're really kind of talking about a challenge where you lose that real-time support. So that access to those 80 and 150 brains and all their experience and all their education goes away for that first hour. And now the astronauts need to take care of and maintain whatever they're going to be flying to in Mars themselves. They got to deal with these anomalies. And the ones that you see in red are the ones that had a pretty good chance of killing the crew if they hadn't figured out and responded within the first hour to the problem. That wasn't done by the 6 people on the space station. That was done by the 80 to 150 people in mission control. And the funny thing about that is you see that over that 20-year life cycle having maybe 1.7 times a year. In the first 6 years of the ISS's existence, it was 3 to 4 times a year. The early stages of shakeout of a new vehicle, for example. And that's going to happen when we go to Mars. That's going to happen when we go to the moon. If we're creating bases on the moon, if we're trying to stay longer, we're going to have hardware, software challenges, anomalies that are going to come up and we're going to have to fix. So how do we deal with that when we have to be more independent? A big part of that, regardless of the propaganda you're hearing about AI right now, is still human intervention. And those humans are getting pushed on by the environment and they're deconditioning as they stay longer in the spaceflight environment. But at the same time, the longer they stay, and they're the ones who have to both figure out what's going wrong and do something about it for those anomalies that are happening maybe 3 to 4 times a year during this mission, they've got to do all of these things that really only humans can do so far. Maybe AI gets there for some of these missions, maybe it doesn't, we're not really sure. But complex procedure execution, the hands that turn the knobs, those are going to be human. The diagnostics, the next works outcome analysis, time to criticality, all of these things require the humans to be functioning pretty darn well. And the reason for that is because if they don't, then we risk catastrophic failure or we risk small failures that can become bigger things and change the mission later. So we talk about risk and we talk about likelihoods of different things going wrong and the consequence. And there are really about 5 things that you can do about risk. One is a lot of the research that we've done to try to understand, hey, where's it coming from? How do these risks actually happen? And once you understand it, once you get sort of the mechanism of how risk is created, you can, in some cases, prevent it. You can, in some cases, if it happens, treat it. Like if it's a medical problem, maybe treat it with medication, and then the consequence gets less. So your overall risk is less if you bring the right medicines, right? Or you treat it as the whole system, and you have to add margin for error for that entire system. That's where resilience, not just of the people and their psychology come in, but also of their context within the larger vehicle, spacesuit, habitat, and mission framework. Where does the resilience of that system come in? We're never going to get to perfectly safe, so we have to, at some point, accept a certain amount of risk. So what's the right level? Well, that depends on how much resilience we build into our system. And what that really kind of depends on is the overall system itself, because the resilience of that system, the things that we build on, how the system works, the basic human needs that we provide, like air to breathe, food to eat, water to drink, they enable crew to respond to contingency, off nominal situations, right? If everything was perfectly nominal throughout the mission, then we could set them at a certain level of performance, and they'd still have to do all these things. They'd still have to exercise, they'd still have to manage their own stress, they'd still have to accomplish mission objectives. They also would still have to do maintenance repair of the vehicles and the key systems for survival. But it isn't until we start to go into contingency domain, which is where all those anomalies that we talked about for the ISS as an example come in, that now all those things have to be done that are really about the response to that. And so when Mark was talking about this, he's talking about unknowns, right? He's saying, well, the unknown unknowns. And when we think about that, we're thinking about what things might happen that can cause risk. How might we design the system to be resilient? And what research should we be doing to try to figure out if we're going in the right direction? And here's the challenge. When Mark uses a term like unknown unknown, what he's basically saying is we can't even imagine some of these things that might occur. So how the heck are we supposed to plan for this? Is there a systematic way to approach that? And so that's what I'm going to lay just a couple of minutes of groundwork on to hopefully set the table for the rest of the discussion. When we think of those terms, known, known, unknown, unknown, these things come from a construct. It's actually a psychiatric construct for behavioral research that was developed in the 60s called the Johari window. And it breaks down like this. The known knowns are things that we're aware of and we understand. When we talk about unknown unknowns, we're aware of them, but we don't understand them. And then there's these two other categories that also have the word unknown in them. There's the unknown knowns and the unknown unknowns. And if this sounds like some squirrely way to get out of explaining the Iraq War a la Don Rumsfeld, that's probably because it is. He used it a long time ago. But there actually are systematic ways to approach these things. And in human spaceflight, what it does is it allows you to categorize your failure modes for the system. And this is the English version of the failure modes for each of those. When we are talking about known knowns, what we're really talking about is we know about a lot of different moving parts that have to fit together. And we know that our challenge is in making sure we take all of them, fit them together appropriately, and make a system that works. And we have solutions for doing that, things like systems engineering. When we talk about known unknowns, we're really talking about research problems. Things like what the Human Research Program looks at. We know we have this problem with SANS, but we haven't figured out either how big of a problem it is or what we should do about it yet. So we spend research dollars on going and doing that and trying to make that into something that we can create countermeasures for or offset. The other two are a little bit more tricky. The unknown knowns in spaceflight come into our domain when we start trying to keep track of all those moving parts when you're operating the system, not designing it, when you're operating it. And all of a sudden, then you start finding those things that don't quite work. The unknown knowns are the ones that surprise you. You probably had enough information in the system, but we didn't have the ability to see it and understand it. And then there's the unknown unknowns. That's the one that Mark says, hey, we didn't imagine it could be a problem. So what are they when we actually put names on them? They have failure modes that we understand, but they also have solution spaces. To deal with the known knowns, we do have systems engineering processes, risk-informed decision-making, and human systems integration. It's about making sure we keep track of all the parts and fit them together appropriately. We create research programs for the known unknowns, like the Human Research Program, and we do a continuous risk management process to feed new things we've learned into how we think about our problems. The complexity ones, the unknown knowns, are really about how do we query complex systems. And a lot of things that come from causal diagramming, network analysis, and discovery science are responsible for structured ways to go and explore that territory. And in the unknown unknowns and the unknown knowns, we both do systems testing to try to, before we go do something serious out in the field, we do test the system a bunch of times. We do drop tests on the Dragon vehicles or Orion to try to see if we learn something or expose something that we hadn't thought of. So all of these are structured ways to approach these things, these failure modes. And what we're usually used to talking about is things like the human research program. We're not usually used to talking about the ones below there, but every single one of these methodologies is trying to surface information, move it from an unknown into a known so that we can take care of it better in our systems engineering processes. That's the bottom line in spaceflight. When everything changes, we go farther out in space, we fly different people, we ask them to do different things for these complex systems. All of a sudden, those known unknowns, the unknown knowns, and the unknown unknowns, they're all changing with it. They're things we can't see. So we're going to be learning this dependent on how much we test, how much discovery science we do, and how much we can actually figure out that we need to work on before we send people to build the base on the moon or before we send people off to Mars. And that's how we structure things to learn from the moon. Just as an example, this is one of the last things I'll say. I'll give you an example of unknown knowns, right? This is from the Columbia Accident Investigation Board. As they looked into NASA's processes, right, what they found were 50 separate systems for the space shuttle with their own nomenclature and process flow. And it was impossible for somebody to look across all those different systems that were about analyzing risk. That is a complex system that we were unable to interrogate. And what you'll see is the part on the bottom that is highlighted, right? Folks misattribute accidents to unknown unknowns, but if you examine the history of these events across complex engineered systems, it becomes clear that the source is most often unknown knowns. The information is in our data systems, but we simply cannot see the relationships. The rise of big data, the rise of artificial intelligence and machine learning means that we have better ways of approaching these, and that we have to create our analysis and our systems to be able to do these jobs better. So we have a chance today. When we think about it with the humans involved, right, good health is necessary, but it's not a sufficient condition for good human performance. Our task performance out here depends on the crew's capability, that individual's readiness, and their health, but it also depends on how functional is their team. Did you bring enough spares to even fix the thing? You could have a perfectly functional and healthy crew who are ready to do a job, but if you don't have the parts for them, that task isn't going to get done. And so good performance itself is a necessary but not sufficient condition for system resilience. You have to consider all of these things as a system. And so I'll leave you with just this thought. Humans are part of that system. They require maintenance repair just like any other spacecraft system. And when you think about resilience of the system, the resilience of the human that we often kind of think about is one piece part of that larger system, but we still need to develop our analytic capabilities, leverage the developing data management capabilities that we have, and leverage the work that we're doing one mission at a time as we go farther out into space to collect the data on how the system and the humans themselves are working and how they're not working, and to feed that forward into the next mission as an iterative way to help get some of those unknowns and move them into that area of knowns. So I'm going to stop there, and I hope that sets the table for some of the discussion on this.
That's great, Eric. Thank you. So while Dr. Rockless is getting teed up, let me engage in a couple of points that came up. One thing that we've kind of neglected to mention so far is that in terms of spaceflight, the real issue for unknown unknowns, actually you alluded to it with the more than alluded to it with the ISS example you started with. The real issue for unknown unknowns and the need for this kind of multi-system resilience is crew autonomy. So to put this into perspective for people who don't have the luxury of thinking about this all the time, like this group, a mission to Mars will be like off the charts in terms of autonomy. About 9 months to get there, 9 months to get back. Due to communication delay, about 40 minutes or so round trip communication with the crew. And that's assuming that they are not on opposite sides of the sun at the time, in which case they're not talking to each other at all. And a lot of supplies and things will need to be pre-positioned and the rest they'll take with them. But in terms of what's available to them, including intangibles like expertise from mission control, boy, they are really going to be on their own. And that's when the idea of unknown unknowns. If you've got 100 people, 1,000 people on Earth to help you, okay, maybe you have some shot at dealing with the unknown unknowns. So that's the context for it. I'm wondering, is it enough to understand that there will be unknown unknowns? I mean, is it like, hey, this is the best we're going to be able to do. We'll mitigate all the known risks to the extent that we can. That will give the crew margin for when the unexpected happens. And then, well, okay, then they're on their own, and we hope we thought this through correctly, recognizing that we haven't thought of everything. So, throughout all these talks and all of our thinking, I'm searching for like, okay, how do we make this actionable? And
Mhm.
relatively few things I've heard that really make the idea of multi-system resilience actionable, right? I
Yeah.
think of all the ways in which it will be needed, but okay, how do we do it?
Okay. So actionable, definitely. I wasn't going for actionable in setting the table. Just
Hmm.
trying to, you know, scope the problem, make sure folks understand, hey, when you do get to that Mars mission, you better have done some things to address the ones that we know if you want to have any margin there, right? So what do I mean by that? We have had a history of human spaceflight where most risk has been dumped on the humans because they're the flexible part of the mission. And you can imagine in engineering the tolerance bands that are required for, how tight this screw needs to fit together and how well does this software need to work and what do these things need to do? Well, humans have tolerance bands as well. And throughout most of human spaceflight, what's happened is not, hey, where is the human most comfortable? It's, gee, Mark, how long can that human actually lay on their back on the launch platform and just suck it up, right? How high can the CO2 actually be in the vehicle? Because it's going to cost us more money or it's going to cost us some mass or volume to make the CO2 levels lower. And as you and I both know, right, that was tolerable for the space station, sort of. But even over that 20 years of the space station, 25 years, they have worked to move those average CO2 levels down from 6 or 7 parts per million down to 3 to 4, right? And what they were doing, the first piece of evidence that they really brought forward from the biological side was, hey, these folks are getting headaches, right? They're those headaches are related to this high CO2 level. We're able to show you that. But then there's this question of, well, headaches aren't that bad. Maybe they can just work through it, right? Well, okay, maybe, but you guys are having them sit up there for 6 months in this environment. And what happens when you go to 3 years, right? What happens when you take away all those people at mission control and you're relying on these folks for that golden hour when something goes wrong to be at their sharpest, even when you do provide them with knowledge augmentation? Because CO2 is not the only thing that goes wrong. There's 1,000 little paper cuts that happen every place that you pile risk onto the human. When you don't provide adequate food and nutrition, when you can't get them up to their allotted amount of water or the required amount of water that they should be getting because it's too much mass, right? When you then add on CO2 and then add on radiation and then add on the isolation and confinement, and death by 1,000 paper cuts is still death, right? So what does it mean that's actionable? Well, there's a whole bunch of first things that are actionable, which is figuring out how to change the paradigm in which we design to make sure that the humans are not the receptacles of risk, but that the system is actually designed around their needs, that you identify the tolerance bands that they have, and you make sure that you're designing to the center of those to the best of your ability. That's where you start getting to margin. And that's where you start getting to the point where you can say, hey, their cognitive function then might be good enough to grapple with these new problems they're going to face.
So I like that idea. That kind of comes back to what I was talking about, a kind of early warning signals, reaching boundaries. Okay, it may not be the only thing that we can do, we, the community, um, but just understanding when you're starting to approach those tolerance limits, because I'm very much attuned to this idea that, okay, what's the big deal? This kind of example. What's the big deal with CO2? We know that astronauts read Scott Kelly's book. We know that astronauts can deal with elevated CO2. Okay, but what about when the next five things happen? You've eroded their margin by permitting this chronic elevated CO2. How can you prove that to make it to get the system to move to reduce that level? Well, you don't want to wait until there's a mishap that actually forces the issue. It's a rhetorical question, but I like your idea. So it may be that some of the things we can start doing as a community are to make ask people to be designers and planners to be explicit about when you're starting to push on the human, you're starting to push on the envelope. And you can do it because humans are extremely resilient and astronauts amazingly so, but realize that that's what you're doing. And so you're
Yeah.
starting to erode some
This is
potential
this is part of the
resilience.
way that we have dealt with human risk to this date, at NASA at least, was to select out as much as you could. It was not to actually design around human need. You selected out human risk as much as you could, and then you started usually in a negative margin situation and said, you guys got to tough through this. So that's what I mean by changing the paradigm. You want to go out there and stay. You want to stay on the moon for longer. You want to have stretched supply lines. You want to be able to go to Mars when you don't have that real-time communication. You need to flip that paradigm on its head and start in positive margin territory, not negative.
Yeah, I think that's another aspect of resilience that we don't think about often enough, which is just not just keeping, excuse me, keeping bad things from happening, but promoting good things. So if everything is working well and you've designed a resilient system, wow, maybe you can actually accomplish more than you planned. Or if there are anomalous unknown unknowns, at least you have not sacrificed a significant part of the mission. Okay, let's put those thoughts on hold for now. Don't go anywhere, Eric. I'm going to turn it over to Dr. Jennifer Rockles. Dr. Rockles is president and CEO of Advancing Frontiers. Before that, she was vice president for products and chief of solution architecture at Teledyne FLIR. Before that, she spent 20 years at NASA with positions that include division chief in the Human Health and Performance Directorate. She's authored many publications in human factors engineering, human machine interfaces and artificial intelligence, telerobotics, bioastronautics, and human systems integration, including the agency-wide NASA Human Systems Integration Practitioner's Guide. She is also has 15 years of nonprofit board experience and is a recognized career counselor and coach. And it's my pleasure to turn it over to Dr. Rockles.
Thank you, Mark. So you and Eric in your conversation teed into mine greatly. So I actually do have an entire slide on actionable things we can do. So hopefully that'll address some of this. Okay. So Eric teed us up well about, showing how resilience is really a systems phenomenon and said, good health isn't the same as good performance and good performance isn't the same as system resilience. But unfortunately, good design isn't good resilience either, right? So the question to you all is, where does resilience actually live in a system? And so, as you just heard a little bit of the conversation around, how do we do requirements and such, we certify astronauts, we validate systems, and we're looking at those against operational limits. What can the system do? What can the human do? But human operational state, right, is dynamic, and it's an integrated condition of their cognitive and physical and emotional capabilities. So In the future, Eric also, touched on this. We're going to be introducing much greater variability. We're going to have wider performance distributions of the people who are flying, different adaptation trajectories, different degradation rates. And so sustained performance for humans and systems really emerges at that human system boundary. So that's what we're going to talk about. Okay, now allocation. We love to allocate things to people. We love to allocate requirements and functions and tasks. Allocation does not equal demonstrated capability. So when we rightfully start from the top, what are we doing? Why are we here? What's the goal? How do we decompose that into a task or a function and trace all the responsibilities and the who's on first? That establishes an ownership, but it doesn't actually guarantee you're going to perform, and certainly not under constraint. So we tend to validate tasks individually. I can do this thing, I can flip this switch, I can check this knob, I can go through this procedure. But our missions demand that we do everything concurrently. So the integrated performance under our finite capacity of the crew would involve things like they'd have to do science ops and monitor the habitat and supervise the autonomy, right? And then respond to the anomalies that Eric was walking through with some kind of delayed or absent ground support. And then we have to sustain all the operations under that accumulating risk and accumulating task load. So humans are the adaptive layer in every complex system, and they come into operations already with accumulated technical debt. Now, what do I mean by that? There's a great set of work that was done by our colleagues at Ames as well, and actually, and he looked at the fact that humans who are operating are compensating really for all of the errors in ideation, philosophy, requirements writing, design test, manufacturing, quality checks of all the humans who worked on the system before them, right? So anything that was left in the system as a residual issue, problem, concern is now facing the operator. And the group at Ames, Alonso Vera's group, they also looked at when we have pilots, for example, who are attributed to, say, a human error, their issues are contributed to human error, and when that led to some kind of a catastrophe. But there are, hundreds of more oftentimes when a pilot intervenes and saves the day. And we really have a hard time capturing that data. But what it shows you is that we're constantly compensating. So to think that you are sending out this perfectly designed system into the world, that the humans have a great shot at working, is just false, right? So just know that this is kind of how we're approaching this problem, to think of this human as the adaptive layer, okay? Now, the next piece is really the layers of resilience and how that functions underneath the degraded capacity. So right here, I've just identified three. So you've got some individual resilience, right? We've talked about fatigue, you might be cognitively saturated, you might be emotionally drained, isolated away from home, not loving your teammates that much that day. And recovery time in this case is architectural margin. You mentioned that word margin in their questions, Mark, but this is kind of where this lives. So one of the things I think I'm concerned about, what we're seeing in a lot of these architectural documents and what we're doing for long duration missions and for commercial crew, is the idea is if they are not busy, they're available to be busy, right? So the notion that you send out the systems in good shape and designed well so that the crew don't have to spend hours upon hours fixing and monitoring and tweaking the system, that's great, right? We've learned that on ISS. We spend so much time fixing ISS that we barely get to do the science, right? That was the story for years. But what it does, that leads to the idea that what we're trying to do is free up time for crew to do other stuff, right? So where do we actually get to be human and recover and rest? So the crew resilience as a team is really about real-time adaptation, right? Without the ground support. Who's got the bandwidth today? Who's got the skill? Who's awake enough to get this done, right? Who's not overloaded? It's how do we pass that conversation around the team and be able to absorb all the workload and handle the anomalies while we're already reduced in capacity with someone maybe down for the count, for example. And then how do you sustain that coordination over the long haul? And then for multi-system resilience, right, we know we're operating as systems of systems, and that risk accumulates. And when one system degrades, everything else has to compensate without cascading more failures. So that's really the challenge for that layer, excuse me. So actionable architectural requirements. This is really slanted towards sustained human performance, less so towards the solution, of grandeur for all multi-system resilience. But one of the things I think we can do right now is start tracking human operational state as a system variable. And we don't do this, right? So we can assign ownership across the systems engineering lifecycle for measuring this and managing it, and specifically, as a variable. And in red and bold here, if this isn't owned, it will get traded away, right? Systems engineering is all about trade-offs. It says, I need this, you need that. We can't both have it for the architecture to close. Who's going to give? Okay. The thing that gives most often is the human, right? So we are, again, squishy, we're adaptable, we'll be able to handle it. We'll just train them, we'll figure it out, right? We have to be tracking this because I want to know who owns the learning when we figure what we can and can't do, right? How are we doing this? Number two, we need to really be demonstrating concurrent performance under realistic crew availability. So validate that integrated performance under competing demands when the crew is already diminished. Okay, we can absolutely do that. We need to protect cognitive margin and recovery time and treat them both as design constraints, right? So engineered systems, like Eric said, they get redundancy, they get spares, but we require protected recovery because we cannot get redundancy and spares at the level that engineered systems can. And then lastly, here I have that we need to validate crew autonomy and Earth independent operations. And we do that by stress testing how flexible the crew are, how autonomous are they in their decision making and their resource management in real time without the ground. So this is an example of what good human systems integration looks like, right? We're treating all the humans, right? Not just the astronauts, but all the humans that are working in and around these systems, starting back way early on with the people writing the requirements, tracking these operational states, all the humans on par with hardware and software with the same rigor that we apply to engineered systems. Okay, and last couple slides here. Where should we learn how to do this, right? Well, we're going to the moon. So Artemis would be a great place. Analog environments, long duration missions, whether here or in orbit, commercial operations are going to teach us a lot. We need to start intentionally imposing operational constraints because human readiness is not a trait that the crew brings with them into the mission, right? It is a condition that's created, right, or eroded by the system they're operating and that we've designed for them. So resilience is a system property, and you got to architect it to sustain it. All right. I'm teeing up for Bill here. This matters beyond just space, but the resilience challenges, right? These are not unique to spaceflight. Healthcare, increasingly, we're facing chronic disease, limited resources, workload overload, right? Complex patient trajectories. So we're moving from treating episodes, right, to managing trajectories of resilience, just like I'm trying to, convey here to really move from thinking about static requirements or even a range of requirements to how do we manage the trajectory of the human and their evolution through the mission. And so my last thought to leave you with here is, resilience fails not because systems break individually, it's because the interactions with the systems and the humans are exceeding our ability to adapt, right? Ta-da. Turning it over to you.
Okay. So that was so rich that I'm still taking notes from some of the comments you made. All right. So, Jennifer, one of the first things that you said was something that I think we've discussed in the past as well, which is resilience is not performance per se.
Mhm.
You want a resilient system because you're sending astronauts into space to perform, to do some things at a at a very high level. But in some cases, I mean, what I think this goes back to my comments on potential changing of goals when crazy things start to happen. Uh, the the needs of the mission can shift and maybe should shift.
Mhm.
And sometimes you may have to sacrifice other goals. Some of those other goals might include long-term human health, right? You might have to sacrifice, you might have to say, well, this is a bad situation, but we're at Mars and we're here for another 6 months. We have to do this thing that is going to give you a lifelong medical issue. But, this is what we have to do for the bigger mission. So I think that's part of it. But in another example that I sometimes use in terms of performance, resilience is not performance. Um, if if you and I were to go on to go down into my basement here on a treadmill, um, I could do 20 minutes on the treadmill if I really, have a good night's sleep and put my mind to it. And you could probably do 20 minutes on the treadmill. The thing is, you could probably come back 10 minutes later and do another 20 minutes. Whereas, like, I'm done for the day. I might even be done for the week. So, the performance of each of us, because I could rally for that, but something is different, right? Something else has gone on that has eroded my resilience, my ability to perform, even though if you measured performance on that particular task, it would have looked okay. So, question from that, do we need to challenge resilience in order to assess resilience? Because this is another one of the things that comes right. What are actionable things? But I also think about, like, well, how do we know if we've designed this system to be resilient? Is it in fact so multifaceted and so different for different systems of systems, that in fact you don't know if it's resilient until you actually hit it with a hammer and see what happens?
Yeah, absolutely. Yes. So, and that's part of my, posit is that we do need to stress things intentionally, but stress them when we're closer to home before we get out all the way to Mars is not the best time to be starting to stress this and looking at this realistically. A couple things I want to say in response. First of all, there's an expectation level that I think needs to be adjusted here, right? We continually expect crew to be able to perform the same they did on launch day, right? And logically, no one will tell you they believe that, but that's how we design the system still, right? So somewhere there's a failure to communicate about what we expect really and what we really build into the system to be able to handle in terms of the realities. And an example, I was just chatting with somebody about this really recently, about, well, we do sims and we simulate tasks all day and then they get really good at it. And I'm like, okay, great. So there's something to be said for, muscle memory, cognitive muscle memory, physical muscle memory, right? We're going to practice this failure in the sim and things are going wrong and blah, 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 we're stressed. Okay, great. But what happens if that happens on day 200 of a mission and you're already sick to death of the person that has to help you do it and you don't sleep well, et cetera, all the things you just mentioned, right? So we are not testing them in the sim under degraded performance conditions at the outset. We are assuming everyone is bright-eyed and bushy-tailed. They came in, they ran the sim. We found some failures. We're going to fix some things and we're going to train them differently, right? So a couple things that were embedded in what I just said, right? We need to, yes, hit things with a hammer, preferably not the humans, but we're going to test the systems by, shaking them up a bit, right? We're going to try to stress them to the point where we see where things fail and how. And we also need to change our expectations around this and give some more flexibility, right, to the way that we're designing an allowance for things to be, in the Eric's category of what we do know and don't know and what we can expect. And if we're going to run somebody through a sim, do it in a few different conditions. Like, yeah, great, get them 8 in the morning, but get them at the end of the day when they're tired or their friends or family or kids have been, like in their face all day and they're just not feeling as 100% as they would have, on day one. So I really want us to do this and think of this as a way to be testing, right? When we do human in the loop tests, they're so pristine and perfect for the data capture that they're not realistic anymore.
Those are great. Those are great examples. I like that. But the example that you're giving, that we expect crew to be fresh as a daisy on day 200, like they are on launch day or the next day. Um, there's a converse example to that, which I'm sure you're very well aware of, which is the second and third Skylab missions,
Mhm.
where the crew is kind of an interesting converse, but by the time the second crew really got in the rhythm of things, they were performing at an extremely high level. So that's a case in which the adaptation worked in their favor. Now the mission was not that long, 54 days, I think, something, or 56, something like that. Not long by these standards, a record at the time, I think. Uh, but then the expectation was that the next crew would be able to come in and pick up right where that other crew left off, and it
Mhm.
just doesn't work that way.
No, it sure
Um,
doesn't. And I think that we, also have a bad habit of saying, oh, we'll address that in training. Okay, so the every crew is different, every human is different, right? And that's what makes our job interesting and fun, is that if this was easy and everybody was exactly the same, we really wouldn't be talking about it, right? But the fact is, everybody approaches and comes at life in a different way. So we have to think about how the human is showing up, right? What the environment that we've designed for them to show up in, and what we're asking them to do when they're there. And that's the part that's on all of us in concert to do together. And when those crews have the training piece, I want to mention just briefly because we tend to think, oh, if there's a hazard, we'll tell them to do this or not do that, or we'll train them to do this or that. And we know that there are lots of folks looking at just-in-time training and how do you do that in a better way. But that entire paradigm needs to shift really in favor of this idea that what happens during emergent issues, what happens during emergent conditions of humans and systems. And so I would love to see us lean into that a little bit more about how we're taking real-time information and data on how are we doing as a team and how are we doing as a person and how are we doing as a system. And look, also, if we had figured this out on Earth, we'd be a lot farther ahead, right?
Yes. So once again, you've caught me taking notes when you turned it over to me. But this is great. So and this will be my segue into Dr. Queel's talk, because one of the themes that Jen, that you had come back to is the idea of variability and figuring out how as things progress, as trajectories take place. And I think about we both have a similar educational background, but I think about trajectories in a state space of performance and behavior, right? The mission state space, the human capabilities state space. I think about trajectories in that state space, which reminds me, brings me back to something that Bill Queel just alerted me to. That there's a thing called viability theory, which is this idea that there's maybe a subset of the state space, let's say a subspace, in which the system is still viable. It can still do stuff. It can still function. And maybe the best you can do is make sure that the trajectory moving forward, the extrapolated trajectory, sits within that viable subspace. And that's not so bad, but it it maybe recognizes that you can't micromanage all of these things. And what you're saying, under emergent conditions, under changing conditions, maybe it is real-time tracking of human capabilities, the capabilities of the mission, resources available, things like that, that would allow tweaks to make sure that the trajectories stay in that viable subspace.
Yeah.
I'll allow you to comment on that before I let Bill talk.
No, I think that's exactly right. And I think that's why we need to start tracking these things as a matter of course, and we don't today. And we always hope that when there's a failure that we put a sensor in the right place to give us the data we need to diagnose it. And then we also have the mutiny of people feeling that they're completely over measured, right, and overwatched. So there's a balance to be had here, right? We are trying to send crew out into space to do work and to live and flourish, not just survive. And that is, like you say, a very multivariate problem. And we are, and as Dr. Poe's going to tell you, we're facing that here on Earth too. So I think we can do better. I think it doesn't have to be absolute, but I think you're right. How do we manage the area, right? Not the line. How do we give ourselves more of a volume to work within, really, right?
Yeah, and you mentioned wearables, and maybe we can come back to this later. But the idea of over monitoring, yeah, of course, nobody likes that. The idea of big brother, astronauts are not very fond of that idea. You do not become an astronaut by having people constantly monitoring what you do. You want some autonomy, and we want to give them autonomy. I take the position that properly implemented, the right amount, whatever the right amount is, of monitoring should give the crew autonomy because they get the information. So don't think of it as mission control, big brother watching. Think of it as a way to empower you, the crew, by getting your own information on your own performance. Now, I haven't had the opportunity to run that up the flagpole and see how many astronauts salutes, but that might be a way to do it. But it also begs the question of how, what do we monitor? What are the appropriate things to monitor? And if you take again the position that we are taking here in general, that we might not even understand the things that need to be monitoring, wow, talk about a non-starter. How do you prove to people that something needs to be measured when it's never been measured and therefore you can't prove that it needs to be measured? So, okay, that's what one of the things I'm drawing on from what you just said. But let's hold it there for a minute, and we can come back to that. I'll turn it over to Dr. Bill Queel. Dr. Queel is a physician in private practice in the Baltimore area with a Johns Hopkins affiliation in general internal medicine. He's worked with the NCAA on injury surveillance, was on the U.S. Soccer Federation and U.S. Lacrosse Sports Science and Safety Committees, was a team physician for Johns Hopkins men's lacrosse and several U.S. Soccer Federation national teams. He later went on to serve as an advisor to several large healthcare organizations to help create value-based care programs to improve clinical outcomes and reduce cost. The overall goal of his work is to help create a technology-enabled, individualized, longitudinal model of medical care to improve multi-scale system resilience. This would be applicable to primary care on Earth and in mitigating the risk of medical events in space. He's the author of the book Dying to Save You, which recounts not only some of his experiences in treating patients. If you read between the lines, you'll see that it's a multi-system resilience approach and reflections on healthcare system in the United States. So, Dr. Queel, the floor is yours.
Thank you for that great introduction, and thanks for having me. Thanks for letting me be part of this this panel. This is it's great for me to be able to share my experiences in primary care here on Earth. You know, one of the privileges of being in primary care is the fact that I've been able to follow a number, quite a cohort of at least a couple hundred people, and I would say high functioning individuals working in complex, high stress environments for many of them over 20 years now. And what I've been able to just basically witness is these individuals that are subjected to often significant adversity, and to see how they handle that. I've seen certainly the emergence of disease processes. I've seen diseases progress, been able to just follow these disease trajectories over time. Some of them end up in collapse and acute injuries, illnesses requiring hospitalizations. Most survive, some do not. So I think a lot about what's going on, what's going just from a biological system, physiologically, biochemically, genetically, what determines all of this. I think, as we'll see, I think it overlaps with the conversations that you've all invited me into in terms of the problems that we're facing in space. So let me start by figuring out how my computer's working. Oh, there we go. So if I may, just a little bit of context, talk about the state of U.S. terrestrial medicine. So 3/4 of us have at least one chronic disease. Over half now have multiple chronic conditions. So we have an epidemic of chronic disease in this country. About 1/4 of Americans suffer from some form of mental illness. This is an interesting statistic. 80 to 90% of adult hospitalizations involve people with at least one chronic condition. So if we're thinking about, as we need to be thinking about here on Earth, because we can't continue to afford this level of sickness, and in space that those hospitals are not going to be available. If we want to be thinking about reducing the need for hospital level care, chronic disease seems to be a place that we should focus. And then finally, we spend over $5 trillion a year in this country, and we have the worst outcomes amongst developed nations, which tells me that this healthcare system, this giant complex healthcare system, is not just marginally effective, it's incredibly inefficient. So what does all that have to do with going to Mars? I think at the very least, we should learn from our mistakes, because while we do have incredible medical care here in this country, as I said, there's things that are not working very well. And I think there's some lessons that we could learn from the current system that will help us move forward. The other thing is, as I said, we're kind of working towards the same problem, right? We can't afford this escalating epidemic of chronic disease, this burden of chronic disease, just a massive requirement that we have for hospitals to deliver care after catastrophic illnesses have occurred. And likewise, that level of care is just simply not going to be available on these long duration missions. So I think we have an opportunity to kind of solve this problem together. So lots of different definitions of multi-system resilience. My view of this on the primary care side is, at least initially, I'm going to refine this later, but the capacity to maintain and return to a state of wellness, and I'll describe wellness, under changing environmental conditions. The challenge here on Earth and in space is the environment is never staying the same. And as those conditions change, they create new inputs to the system. I would argue probabilistically, those changes take us away from a state of wellness and coherent function and efficient operations. Usually surprises aren't great, and we have to navigate them. Sometimes they're good. We all like a nice surprise. But a lot of times they put stress on the system. Let me talk a bit about wellness and sickness again from my perspective. I look at wellness in my patients as it's a state really of high functional capacity. These are individuals that can really accomplish a great deal of work, and not only just they can do it, they can do it very efficiently. So when you look at time to task completion and what some people are able to do in relative time complaints, people that are well are able to do that. You'll notice I'm using the word wellness and not health. I look at health as synonymous with resilience. Mark, you brought up the WHO definition early that health is not the absence of disease. Wellness, to some extent, is the absence of disease, but again, it's really as much about performance. Minimal discomfort in a state of wellness. Physiology is fairly predictable, and that's useful in terms of me being able to plan what tasks I am able to perform. And there's generally low resource utilization for people that are doing well. On the other hand, sickness is a state of poor functional capacity. Very hard to get a lot of work done when you're sick. It tends to lend itself to operational inefficiency if you really do try to muster through it. I know that certainly in my medical training, when I wasn't feeling well, it was very difficult to maintain a high level of efficient performance. There's often significant discomfort in states of sickness. Interestingly, physiology becomes somewhat unpredictable, particularly as you get in a kind of hemodynamic instability and high levels of sickness. It's really difficult to predict exactly what's going to happen, and we run into trouble or challenges when we prescribe a drug. We think it's going to, I don't know, raise blood pressure and it falls further. So there's an unpredictability to sickness, which is interesting, if nothing else. And obviously, we tend to utilize a lot of resources trying to care for sick people. I want to talk a bit about stress and disease, and particularly stress response. As I said, when environmental conditions change, we're subjected to new inputs, if you will. Often they pose a challenge, not necessarily a solution. So we can look at environmental stressors on the end just in a global sense. I'll talk a little more in detail in a minute, but just environmental stressors, stress in the general sense, leads to a stress response. And we know quite a bit about the stress response. It's been studied for decades in human physiology, and now neurobiology is very interested in the stress response. In fact, some have coined the term neuroendoimmune response because there seems to be there is this relationship in somewhat of a causal chain fashion from the sympathetic nervous system, which gets activated very quickly, followed by the endocrine system, epinephrine, norepinephrine, or adrenaline. And then if left unchallenged, and this is important, like the stress response is not a bad response, it's life-saving. The problem is if it goes on too long and you start to get prolonged secretion of stress hormones like glucagon and cortisol. And ultimately, I think where things start to really go off the rails is when the immune system becomes dysregulated. And we've seen that in COVID with cytokine storm. That becomes a challenge for all of us. We know that stress, ultimately, there's a lot of evidence in terms of stress to individual chronic diseases. When you look at each disease, there's a stress relationship or causal relationship, really, to many of the diseases that we see. Now, one of the things that, as a primary care doctor, I'm less concerned about exactly what disease any of my patients get. I'm concerned about any disease. So the further to the left on this diagram are upstream from this stress response, the better. And of course, people living with chronic disease, we try to manage them as best we can, but again, unmitigated stress often leads to acute illness or injury and often lands them in the hospital. So I want to talk a bit about system-environment interactions. Jen had talked about this, and stress comes from our environment. I should mention, I don't want to get into details here, but we all have a set of genetic variants that render us vulnerable to selective stressors. Some of us seem to have a stress tolerance to certain stressors and others don't. This gets to the idea of individualized care, because what is a stressor to me might be nothing to you. But with that being said, it is ultimately still the environment that starts to push us, that provides this forcing function that generates that stress response that we need to somewhat, I think, model. Knowledge graphs, Eric does a lot of work with knowledge graphs, and I will go through my simple kind of model that I use, and my colleagues have seen this before. But when I'm a big believer in the physician-patient relationship. This is where this network starts in terms of understanding how the environment is affecting my patients. And the key component to this relationship here, primary care physician on the right, the patient on the left, is trust. I brought this up on many occasions. Without a strong, trusting, solid, symmetric, balanced relationship, nothing else matters. So I spend quite a bit of time ensuring that this is developed early and strongly in my relationships with my patients. Very simply, if my patients don't trust me, they're not going to confide in me. And when patients talk to me, that's data. That feeds the algorithms and the models that I'm developing here. And I need to know basically everything. And I need to make sure my patients feel comfortable telling me anything that is relevant. It works the other way too, because if patients trust me, that they know that when I'm going to make a recommendation about reconfiguring their environment, which means changing their behavior, they're more likely to be compliant with that recommendation because they know it's coming from a good place. Patients, humans, are multi-scale systems. Starting at the bottom, we have, again, a set of genetic variants. We all have 20,000 genes. They're all different. They interact to form molecules, which form cells. Those cells aggregate to form organs, and those organs all interact to form us and to help us perform in the outside world. But this cascade does not stop with us. Humans organize into families and live in homes, which has its own environment. Families and homes exist within communities, and those communities exist within society more broadly. So we talk about multi-system resilience. This is a multi-scale system. So we're talking about resilience of really this entire kind of stack here, with the patient sitting in the middle. But really, you could declare any of these levels to be a system class. And for example, the family and home, this would be the analogy of a spacecraft and a crew, in which case that becomes the system itself. And then we have to look at that system. We could model that system relative to its environment. But we can look at this at any scale. As I said, this multi-scale system is subjected to environmental stressors, environmental inputs. Epidemiology colleagues would say environmental exposures. But this is the world that we live in. Everything's interacting with everything at multiple scales, which makes this very complex, makes it a complex system. They're also bidirectional because we kind of create our own local environments. The food that I choose to eat turns around and has, effects on my genes and my cellular function. So to some extent, I create my own problems and oftentimes create my own diseases. The beauty of that, though, is it says we actually have an opportunity to modify, change, or what I like to say, reconfigure our local environment. The problem is, or the question is, we just don't really necessarily know what to do. We're all kind of flying blind in terms of what do I actually need to do to remain well. So as a primary care physician, this is what I'm looking at when I see my patients. I'm looking at them as a component of a multi-scale system subjected to all kinds of environmental stressors, with everything interacting with everything at every scale. The good news is I have help. I'm not alone here on Earth. I have an entire U.S. healthcare system at my disposal. I have lots of local resources in my practice. If I get over my head, I can call one of my specialists to bail me out. They have lots of resources at their disposal. If they get overwhelmed, and ultimately we can send people to the hospital. And then we can utilize many, many hospital resources. So this is great for us here on Earth, but again, the cost is becoming unsustainable to rely simply on the right side of this graph here. It's just too expensive. It's arguably not right either, because we have a lot of sick people with chronic disease. It would be maybe a much better society if people were more well than sick. But again, in human spaceflight, we're not going to have all of this. Eric, I think Jen, you're all talking about mission control and the idea that that we have these resources available, subject matter experts, the specialists. We rely on them. This idea that you have a crew that's in an environment that is self-contained without those available resources is nothing short of daunting. Here we go. Here's an example of maybe a healthy patient, a resilient patient, somebody who's well functioning at a high level. What the lines, darker lines represent are stressors. Doesn't mean that the other lines are not there. Again, they have connections to their environment at all levels. But when I'm looking at somebody, I'm trying to assess what are the big ticket items, what are the stressors that they're dealing with. Now, in this situation, most of my high functioning patients are exercising, so they're subjecting themselves to physical stress. That's a good thing. A little bit of stress is good. We're adaptive systems, and we can actually increase our functional capacity, strength, mitochondrial function, energetic capacity. And then psychologically, again, learning and psychological stress, or at least cognitive load, is not a bad thing. This is how we adapt. However, I will sometimes get a patient that looks like this, where they've got lots of stressors, and things tend to become very unmanageable. Again, everything interacting with everything, they're getting hit from all angles. And not surprisingly, everything gets pushed through the system. I'm, utilizing local resources. I've got, calling to my specialists. Sometimes they end up in the hospital. And this is what I might refer to as a complex patient who has somewhat of a complex network. Now, I want to share with you the way that I've been thinking about this, something that kind of dawned on me, I don't know, a number of years ago, that I think still holds. I haven't proven it not to be wrong. I'm working through some of the details of it, but it certainly is a way that I view my patients in a state space type of fashion, and where I can start to understand disease trajectories. And broadly, and I say that broadly, I look at structure versus function. So the most minimal model for me with any complex system is at least break it down into structure, and that structure means basically the network architecture that we just looked at. Generally can look at it as more simple to more complex. Complex doesn't mean bad, by the way. The richness of somebody's network is also the solution space when they have a problem. So it's not a quantity issue. It's not about network density per se. It's about the quality of those interactions with the environment, and the quality of the resources available. And keeping in mind that what might have been an asset at one point in my life, as I get older, that might not be an asset, and that could become a liability. So even the nature of the interactions, even if the interaction stays the same, the quality of it could change over time. But nonetheless, there is something to be said about what I would call the complexity of the network. And then, of course, the wellness to sickness spectrum on the horizontal line there basically represents what I had shown before. Now, I look at this, it's kind of the upper left part, the quadrant. This kind of breaks into 4 quadrants, is where I think most of us like to be. And I would say most of us that are doing well seem to live. And this is an area of relatively high performance. We can live in very complex environments. We can perform at a high level and really do well. We're not sick, performing at a high level. And this can go back and forth, right? This is an area, maybe we could call it homeostasis. My mechanical engineer friends call this elasticity. There's some interesting parallels to the stress strain curve here. But this is a place where we want to be. Now, as we move forward over time, and maybe we accumulate some more connections, often those that provide stress, we can get pushed further towards the sickness, less coherent function, some physiological dysfunction, maybe pathophysiology. This is where I meet people in a chronic disease state. It's a maladaptive state. It's a state of strain. There's a point as if the stressors are not mitigated, the human body is remarkably redundant. There's a lot of redundancy built into that system. But as Mark alluded to or said, you start to run out of compensatory mechanisms. That solution space can get used up, it can evaporate. And as you start to lose those compensatory mechanisms, we get pushed towards potentially a threshold here into acute illness or injury or a state of kind of rapid collapse. Now, this is often where I meet people in the hospital, where they, honestly, one of the good things about a hospital is you get removed from the environment that caused you to get there in the first place. So there's an element of simplification and probably evolutionary, from an evolutionary standpoint, you get sick, we're supposed to either crawl into our cave or crawl under the covers and not come out. We don't do that because that's not a culture that we live in. Probably to our own detriment, by the way, because I think when we do get sick, we probably should contract our configurational space. We should detach from certainly the stressors that cause us to get there. And we might do it temporarily. And if we learn lessons, we might do it permanently. But either way, most of us, if we don't die, we will settle out and start to return to a state of wellness. And then we will actually embrace a period of recovery, which could include physical therapy and actually rebuilding capacity, right? So now we can, once I've kind of hit this kind of low point that I've kind of healed, now I can actually start to rebuild, whether it's my, again, functional capacity, whether it's my social network, my job, I can kind of get back. And if I'm lucky, I can get back into the upper left quadrant. I think it's important to notice that, that's not the same place, by the way. It might be the same place in the state space, but it's not the same network. One of the things about this is all about network reconfiguration. So the person that I was when I was up in that left upper quadrant before may be different than the person that is now. So I kind of start to think about multi-system resilience as this capacity. It's really a capacity to reconfigure the network architecture, mitigate the stress response, not only necessarily the stressors. Some people can operate in high stress environments without really generating a stress response, and return to a state of wellness. And that's basically the idea of running that cycle. Can I get back to that left upper quadrant? And it's a capacity issue. As I said, that takes energy. One of the things that I think aging represents and frailty is this kind of contraction of that configuration space, that level of complexity or structural richness that we need. Because remember, complexity is not bad. It's a solution space. We need resources internally and externally. If we lose them, then we lose the capacity to adapt at all. And then, when we're confronted with the unknown unknowns, we don't have a capacity to adapt. That to me is when we get in trouble. Mark talked about viability theory, and I think that's applicable. I think the goal is to live in what they call the viability kernel. And then there is a viability margin that can get eroded. And so I think there's some opportunity there to utilize some of these, this math to understand this. I think the process of reconfiguration seems to have two phases. One, I got to deconstruct the old network that got me in trouble, and I got to reconstruct a new network under new conditions. Because remember, conditions have changed, so I need to adapt to the new conditions. A really interesting phenomenon of biological systems, something called allostasis. Mark and I have talked quite a bit about. It's a model of predictive regulation or predictive adaptation, anticipatory reconfiguration. And what the model says is that we actually have the capacity to predict at least the near-term future. Now, this could be cognitive. I often think about the weather. I'm going to reconfigure. I might reconfigure my if I put shorts and a t-shirt on and it looks like it's snowing outside, I might go back in and reconfigure my outfit so that I can actually stay warm in that cold environment. Organisms do this, I think, at a subconscious level as well, and there's some really interesting work that suggests that we can actually do this, which kind of begs the question, if we go back to this kind of theoretical state space, can we run this cycle? Can we run cycles of deconstruction and reconstruction? Can we continuously modify our relationship with our local environment? Can we rearrange resources in such a way that we actually reduce the level of dysfunction, sickness, and kind of head this thing off at the pass? And if we do it at high frequency enough, maybe low amplitude, is it possible that we could stay left of that vertical line altogether? In general, left of that line is a state of wellness, right of that is a state of sickness. I actually think this is true. I might be a little bit of a dreamer in this regard, but I have seen this to be true in my practice. And I am convinced that if you can do higher frequency, lower amplitude changes to our environment / our behaviors, that we can actually return to a state of wellness before we actually experience chronic disease or collapse. So that speaks to this idea of not just returning to a state of wellness, but can we actually maintain a state of wellness over time in an environment that's constantly changing and causing stress? And I think the answer to that is yes. And then that begs the question, can we design? Can we build this as a design feature that we create this multi-scale system? It'd be highly dynamic, but in such a way that the solution space is available enough that we have enough configurational richness that that the astronauts, in the case of a spacecraft, have the tools to figure it out. We won't be able to tell them what to do. They're going to have to figure it out, but they've got to have the resources to be able to do it, and maybe some technology to help them. Let me talk briefly about technology. This is a schematic that I've showed before. It's actually the schematic of a platform that I would certainly love to have here on Earth in my practice. To the left is some administrative stuff. That stack of peach-colored nodes is really various multi-scale measures from genomics at the bottom through cellular metabolism, physiology, human performance measures, up to environmental exposures and broader information as far as health is concerned. That can all go into a repository, and now with AI doing what it's doing in partnership with us, so we can all learn together. So it's not really physician-patient relationship anymore. It's physician-patient AI triad. And we're all learning about everybody over time. And that keeps all of us on the same page, and I think would allow us early detection, early warning signal detection, and more rapid changes in environmental relationships. This, of course, is a lot of what Eric, we've talked about. These are the kinds of systems I think will allow us to do the monitoring, subject to the astronauts actually agreeing to it. But I think you're right. I think if they know it's part of a system that they trust, back to the trust word, that this will actually help help a crew actually maintain autonomy with an onboard system. So I do think that with the right technology and the right clinical program, we can not only make the world a better place here, but we can get a crew to Mars and back safely. Thank you.
Wonderful, Bill. Thank you. So you've given me a lot to think about there. I've got a lot of notes, but let me point out, here's what's going to happen here for the next 40 minutes or so. I'll talk to Bill briefly, but during that conversation, I want to broaden that. So Jen, Eric, you guys can start to feed into this and make it a more broad conversation for the next 10, 15 minutes or so. And then I'll turn it over to Ivan, because he is fielding some really good, challenging questions. And frankly, I want to hear how the three of you answer some of them. So, Bill, I think the systems approach has really become very apparent in what you're talking about. And I think I appreciate it when I go to my primary care physician and the practice itself is set up to start asking questions about my stress level, about my environment. Do you feel safe at home? There's a lot of them are kind of boilerplate, but just the idea that seems to be at least starting to take hold that, yeah, okay, we understand environmental stressors, your social life, your work life, all those other things. Yeah, geez, do you think they might actually have an effect on your health? And I took on my new medical care provider about 4 years ago at a time in my life that was extremely stressful. So there's absolutely no doubt in my mind that that's what was going on. So that's the kind of thing that I like. I think of that as largely kind of on the input side of things. What about the output side? So the idea of changing goals, the ability of how many times do you see a patient and you have a discussion with them that goes something like, well, that's really more aggressive than I need. to be able to accomplish the things that I want to accomplish in my life, given my age, given my resources, whatever it might be. That's a very space flight type question as well, right? Because we cannot possibly on a Mars mission, it may very well be possible, as I've mentioned before, that we cannot maintain crew health and well-being at their pre-flight level, at the level that we would like to. They just have to take a hit. But that's the price you pay for going to Mars. That's a very, that I think that well, do you incorporate that kind of thinking in your care, and how so?
Yeah, no, for sure. I think I see it mostly again over these long time frames where we're all aging, right? And my patients are aging, I'm aging, and in fact, I have these conversations very often with patients of mine that they want to maintain the same level of performance, functional capacity they did 20 years ago. And to some extent, listen, this is where exercise becomes this foundation of capacity, building and kind of maintenance, which is why exercise is so important. Now, a lot of this, my big concern, particularly in spaceflight, is the more rapid depletion of functional capacity, and a lot of that's at the mitochondrial level. Maybe Eric, you and I have talked about this a little bit, or kind of going back and forth. That I think mitochondrial function is something that we have to really, really focus on, because at the end of the day, that's where the energy for adaptation comes from. If we lose those energetics, then the capacity to adapt really starts to decline, and then we cannot reconfigure based on changes in the environment. But no matter how hard you try, or we try, to offset that decline, the aging process, there is an aging process, and we're not going to live, forever. And the healthiest 90-year-old is not as healthy. I should say the performance of a healthy 90-year-old is not the same as the performance of a healthy 20-year-old. So we need to respect that, and we have to build that, I think, into the models. But yeah, there comes a point in time where I have to suggest to my people, and I'm trained in sports medicine, so my nature is not to tell anybody they can't do something. And in fact, I rarely say it in that fashion that you really shouldn't do that anymore. It's maybe we should think differently about how you are exercising, eating, how you are arranging your day, how you are arranging your work schedule, because it's clear to me that you're on a trajectory that is towards sickness, and if you don't change something. And this idea of letting go, detachment is the hardest part, I think, of reconfiguration, because we tend to hold on to things. So a lot of my conversations are about subtly having people change their goals without telling them you shouldn't do that anymore, because that's not what they want to hear. So I like the term reconfiguration because there's a positive aspect to it. But at the end of the day, you're right. It is saying, this is just not something that is really a good idea anymore. I think we need to change our objectives.
So I'll say one more thing for you directly, because I can't resist, but then everybody can jump in, because what I'm getting at is you using the term wellness a lot, and I'm curious about what your definition of that is, because I think that relates to multi-system resilience, which is then how we can open up this discussion. But I'm also wondering if this quote, which I know I have shared with you before, has any bearing on your idea of wellness or medical care overall. And this is from Voltaire: "The art of medicine consists of amusing the patient while nature cures the disease." Right? So how much is it your job just to advise them on how to simplify, let go of things, provide a buffer, a cushion, do more of this, do less than this, less of this, and then let's just wait for nature to take its course in a good way. And is that an approach that we should take in spaceflight?
Well, the beauty of biological systems is they heal. I mean, we don't really necessarily know what that process looks like. My experience is if I can just get people to disengage from relationships, behaviors that are leading them in a disease trajectory, then I don't necessarily need to worry about getting them better, right? The biological systems are going to heal. They're going to kind of return to this state of wellness for reasons that, we can ponder. But most of what I do is exactly that, is kind of helping people get out of their own way, and allow nature to take its course. There are things that we can do to facilitate that, and there's a lot of support that we do in medicine. And we look at our conventional medical system. We need, for people that are far out on that sickness spectrum, they won't survive without support. So, and again, these are all just resources that become available. So it's part of the configurational space, but it's a good one, right? And we need to support people until they can get to a point where the healing process takes on a life of its own, with some support of physical therapy. And I was obviously a former physical therapist, so I enjoy being part of that healing process, and restoring people to not just a state of wellness as non-sickness, but a state of wellness of high performance. And people can get back there. I've seen remarkable people that I didn't think were going to survive, who end up going back to run marathons. It is just a spectacular capacity of the human body to not just survive, but to actually thrive. So the more we can understand that, the better.
Yes,
Mark?
Eric, I was going to call on you anyway, see what you think about that quote or something else.
Well, given that Voltaire died in 1778, the real question is whether you want to go back to the medicine, of that century, and recognizing that, we have made lots of advances in lots of places and still don't know things perfectly. Since Voltaire died, right, life expectancies in many, many parts of the world have improved because of things like sanitation, hygiene, medicine as one of those things. And going on to the moon and Mars is only possible because we leverage those changes. We leverage the things that we've learned along the way. So, I tend to struggle with Voltaire's quote in a modern day sense. But I do think that there is a little bit of truth in it, in the sense of, yeah, the body is self-healing in a lot of ways. But I think what we struggle with in spaceflight is sort of a slightly different bent of that, right? We all are still wondering what changes our adaptation and what changes our pathology. And to rely on, the body will take care of itself, relies on the assumptions that we make about the exposome, the environmental exposures that are what we evolved in and live in on Earth, right? We see changes in the immune system. We see cell populations change and decrease, NK cells, T cell function changes. We see changes in all sorts of different things in spaceflight in our systems. And until you kind of settle into what's the new normal and really document that, it's hard to say, well, the body will just, fix itself. We don't know where things plateau. We don't know if partial gravity on the moon or Mars is going to stop muscle atrophy or reverse it, right? And discussion about that Bill brought up about mitochondrial function. That's where you're losing a lot of your mitochondria, is in the muscle loss. And so, this is part of some of that. Can we rely on those old adages? Can we do things the way we've always done them before? And the answer is, I don't think so, right? We've got to continue learning about what's adaptation and what's pathology, in order to settle into what is the new paradigm for how we function.
Oh, but it's such a great quote. Now I have to stop. Now I have to stop using it.
No, you just use it for people who are 300 years old.
Okay. Fair point. Jennifer, you had unmuted.
Yeah, I was going to answer Chris's question, but it's not directly related to what we were just talking about. So happy to hold it.
Yeah. So Ivan will get to the questions in a minute. But Eric, what you're saying reminded me. So it sounds like what you're calling for, an appropriate level of intervention. And we're not just talking medical now, right? I want to expand it to the multi-system aspect. So it may not be sufficient to just design a mission properly from the outset and then let go of it, and then let the crew, with the proper monitoring of on their own, let the crew be autonomous. So it's the analogy to your idea of more modern medicine does allow for appropriate interventions at specific times.
Well, what we all struggle with is how do we know what's an appropriate intervention, right? We know it on Earth in many areas of medicine and healthcare because we have huge amounts of data. And in space, we don't have huge amounts of data. So we're not able to tap into an actuarial sort of understanding of what is the appropriate intervention. What does appropriate even mean in this case? And I think one of the biggest problems that we have is our insistence on limiting ourselves to a mission-centric framework. We should be thinking about these as campaign that goes from low Earth orbit to Mars, because we're not going to be able to gather the information on what is pathologic versus adaptation in simulations. We're not going to be able to gather the information that we need to start figuring out what's adaptation or pathology in low Earth orbit if we're planning for changing between low Earth, a spaceflight microgravity environment and a partial gravity environment. So we have to be looking at each of these missions as a contributor to the larger set of knowledge that we have. That means allocating mass, volume, power for sensors and detectors and things that tell us what's the state of our environment and what's the crew operational state. And in today's framework and in the framework of the last 60 years, nobody at NASA thinks of monitoring as a countermeasure, right? I spent years trying to convince people that monitoring is a countermeasure. It is how you feed forward information. It's how you capture the information about today. It's also how in a given mission, you decide whether to do an intervention, whether to use a countermeasure. And it's also how you capture information about how effective that countermeasure was, so that in the next mission, you're feeding that information forward. And if you keep it in a mission-centric framework, just this one mission, and then we move on to the next thing, there's no reason to capture lots of that information. But if you're building a database for the future, because the missions that are coming afterwards need to build on this information, then you have to treat monitoring as a countermeasure, and a really important one.
So we should, given the relative lack of experience in space, fewer than 700 people in 65 years, we should be treating every mission as an experiment.
I believe we should be, yeah.
Implicitly. I mean, we should explicitly think that it's an implicit experiment.
And it's not necessarily a hypothesis-driven experiment,
Yes.
right? It is discovery science.
Yeah.
It's discovery science. It is observational science. It is gather as much information as you can, because we don't know a priori what the most important parameters are.
Right.
So if you capture that serially in a standard measures type of way throughout campaigns of missions, you can start to actually analyze and look at the data as a whole and start to figure out, hey, maybe some of these things are knobs we can turn for countermeasures or health.
So this requires, on the science and research side of things, especially in human research, expanding our conception about what is an allowable approach to science. This was the topic of one of our previous mini symposia a year or so ago on statistical approaches to that. It may just not be feasible to do what we would consider a laboratory grade, let alone certainly not a double-blind controlled study of a lot of the things that we study in space, because you're just not going to ever have the appropriate number of people for those conventional statistical approaches. That doesn't mean that it's not worthwhile, and it doesn't mean you can't get something from it. It's more in the form of like a natural experiment. Things happen anyway. Let's take advantage of measuring them as best we can.
Yeah, Mark, can I comment on this? I feel like a lot of times we do ourselves a disservice by thinking of it either as a science experiment or part of the engineering build. And what I think we're trying to do is move the thinking around science and discovery into the parts of engineering that are responsible for the system life cycle of the vehicle, right? So stop thinking of it as a payload that you're flying to collect data, and start thinking of it as part and parcel of how you design a good system, which is to be measured and monitored, not just for system state and failure, but also for opportunities and consequences and all of those things. So I think that's where it runs a risk, is because it's thought of as something else that is a nice to have and it's a tack on, as opposed to part of the fundamental architecture of the system mission.
That's a really great idea, and completely, I say Eric approves. I'm that's so good that I want to end this discussion on that note. We could go on, and I have a feeling that the next time we are all together, we will go on and on. But for now, I'll leave that thought hanging because I think that's a really great one. Because like I said, we have a number of really great questions, and we'd like to respect everyone's time. So we've got 20 minutes in which to do it. So I'm going to turn it over to Dr. Padilla to curate and read us some key questions. And anyone can jump in to answer anyone unless it's been directed to somebody specific. But even then, if you have something to say, feel free. Ivan?
Okay, thank you, Mark. And again, to our speakers, we do have a number of excellent questions. We'll see how many we can get through. The first one is from Chris, as we've alluded. It's a question on, as Eric talked about, the increased requirements for autonomy is, could we ever design, and should we even try to design, for fully autonomous systems that could, in principle, cover for an incapacitated crew throughout the life of the mission? And Jennifer, I think you wanted to take a stab at this.
Yes. So I did want to take a stab at it. The answer was not yes. So we do have already today levels of autonomy in the crew systems, in the flight systems, right? We want an increasing amount of ability of the crew to be able to be hands-off when it's day-to-day monitoring of systems, right? Where can we build, autonomy into operations of life support systems and spacesuit systems and whatever, what have you. So that is already in the plan to be able to do that more. Maybe decision aiding, you think about AI and all the things. There are places where we would do that mindfully and always with the human in the loop. And the idea is, where can you kind of port the Earth-based folks that actually kind of operate that way today as the background AI, right? And the background autonomy, right? They're deciding and they're churning and they're going, hey, crew, how about this, right? But you don't hear the massive discussion and data that they got a chance to take a look at before they came to you with an idea. So we're trying to kind of package that up into the vehicle and be local with the crew. That's part of it. When it comes to a person being out of commission for whatever reason, then it comes to understanding what the tasks and the functions of the crew members are, that we can transition to automated steps, right? And if we can, where and why are we not adding that in as a natural backup, or say a dissimilar redundancy in the first place? So I would take the approach that you would look at what the functions and the tasks are that are required of the crew, and which could be allocated to autonomy, and where it is most effective from a cost and mass and volume and in complexity standpoint to automate some of those, either as a primary or as a backup for when crew are not around. But so I'm more speaking to the approach that I would take to figure that out. I'm not necessarily saying it's a great thing, en masse, right?
I'm going to say, if we could design an autonomous system that could completely cover for an incapacitated crew, what the hell do we need the crew for? And the simple answer is, I don't think we can do that. And I don't think we will be able to do that anytime soon. We have designed systems and put them on Mars that are pretty autonomous, not 100%, but pretty autonomous. And those things have gone and scooped up, a few grams of material and left them on the surface for somebody to come pick up, right? Over the course of 3 years. And in 1972, when Apollo 15 went to the moon, they brought back 315 grams of moon rocks and dust, not grams, kilograms of all that stuff, and traveled 35 kilometers. And the rovers have done that in several years, and we've never gotten the things back. So when I think about autonomy, right, like when you frame it as, could it fully replace the crew? What you're really talking about is, what are your mission objectives? And could you do it in an automated robotic sense? And I think the answer to that is we're not even remotely close to that right now. So like Jen says, where can we put in autonomy to unload the crew so that they can focus on the mission objectives, or they can respond to anomalies without the real-time support of all those people at mission control? Those are laudable goals. But if you could really design the next Mars rover to fully replace the human crew and bring back all the rocks you want, why are we sending humans?
Well, there's also the opportunity, right? Not just the anomaly, right?
Mhm.
There's the occasion on I guess I think it was Apollo 17. But hey, there's orange soil. It's like,
Mhm.
hey, wait a minute, don't move it. Let me see it. And okay, sure, you could program a robotic system to look for those unexpected things. But geez, humans are so good at that. And that, in fact, we are sending them to a new place specifically to find the unexpected.
Yeah. One thing I'll say is I think that there's a lot of places we can and should improve autonomy. There are currently today disagreements between NASA and SpaceX about, hey, should the piloting and the landing be something that the crew can do, or should it be the vehicle autonomously, right? And Russians have done autonomous docking to the space station for years, and the US has typically not done it. So it's almost a matter of philosophy to some of these extents, right? Like, to what extent is autonomy appropriate? And that really is a question of what's achievable. And I think a lot of folks, when they think about autonomy in space, think a lot more is achievable right now than it probably really is.
So there's a small team of us at Hopkins at APL working on the idea of autonomous human machine teams, which puts another kind of overlay on it, which is not just autonomous human crews with a little bit of robotic assistance and not autonomous robotic teams, which is what people tend to think of, and the humans just watch them and supervise them from afar. But really, the robots and the humans synergistically working together like a good human team would, which requires them to have a shared mental model, be on the same page, all of that kind of stuff. But and modulate what they do based on real-time information about what's needed and what are the capabilities, which then requires monitoring. So it gets complicated really quickly. But I think that should be where the future of this kind of thing goes. And obviously for Mars, it would be tremendous.
Yeah, and I'll just add, Mark, that remember, we then have to monitor those systems. So I'm not responsible for Eric if he goes down, right? He's responsible for himself first. Then if he can't, I will help, right? But there's an outset understanding that I've got to take care of the robots because no one else is around to do it, right? I mean the crew. So there is a perception that the robotic systems, the autonomy systems are always up and working, and that there's scheduled, planned maintenance. That would be lovely if that was actually the case, right? But what is the hidden workload of taking care of each other and also taking care of our systems?
Yeah, well, first of all, I'll point out that long ago, I think all of us gave up on trying to monitor Eric. Uh, but the but yes, the idea of
More sensors.
when the humans are in the loop, it is the it is the humans who will, among other things, maintain and possibly enhance the performance of what we would call robotic. The line starts to blur, right? So it's not this clear separation of human machine, right? It's the human's function to be able, it's the machine's function properly. They give the humans autonomy and room to maneuver, and the humans then can maintain the machines, which then in turn give them more room to maneuver. It's a virtuous cycle done correctly. Okay, Ivan, back to you.
Excellent. Our second question is from Michael. So, in Mark's opening remarks, he mentioned that we don't even necessarily have a good definition of resilience. So Michael has a question, the semantics here. So resilience in humans refers to the psychological and physical capacity to adapt, recover, or grow in response to stress or change. Perfectly valid. And he continues, systems don't have cognitive control in physical action. So in that sense, it is only the human that has resilience. Is resilience a concept that generalizes across people and machines, or should we be using separate terms for these? And I suspect that Bill might have something to say about this.
Well, that is a really good question.
I personally think that resilience is resilience. If we define it, it should apply to any system. And I think there are patterns of behavior and performance of systems, regardless of whether they're mechanical or biological, that are modelable, trackable, and when we see the resilience is being eroded, if we see performance is being degraded, that we have interventions, countermeasures that can effectively restore function before collapse. It's a failure, prevention. So my off the cuff as a non-engineer says that I think we should be looking at the similarities and what are the general properties of resilient systems and how they apply to both biological and mechanical systems.
I want to jump in on this one because I think that to say that resilience in that capacity doesn't apply to machines, I think it misses some things. We all struggle with machines in our society with things like planned obsolescence, right? Somebody designed this damn thing to fail in a certain time frame so that you'd have to go buy a new one, right? We all know that the cars that were made back in the 50s and 60s, they had a lot more resilience if people hit them, if things happened, right? But we changed over time how we design and build things. There's a lot of companies out there that build machines to a certain level of resilience, and then they want you to throw away and replace the part because that's how they make money, right? And you could use better materials or you could use more quality things and make certain things last longer, but then, the company wouldn't make money because you're not buying more parts. So we all struggle with resilience, I think, in machines in our daily life. And the resilience of how those things are designed is a decision. It's a design choice in many cases, right? You're going to spend more money on a well-designed system, a quality system. But, sometimes we buy for quality because it is more resilient. And I think we need to keep that in mind. We spend billions of dollars putting people into space. And we're trying to get that quality of that whole system as good as possible. We're trying to make sure that that system is resilient. And yes, there's a human cognitive component, but I think resilience very much applies to machines as well.
So let me expand on that a little bit and then unfortunately cut that line of conversation short. Yes, because I get the last word on it because Ivan still has some more questions I want to get through. But this reminds me of a little written conversation, dialogue that we were having when we were putting the white paper together. It begs the question, Eric, you're talking about car manufacturers. What is the system? What is the system that we are considering? Because then you might say, well, we need to think of this larger. And if we include as the system, the viability, the economic viability of the car manufacturers as part of the national economy, well, now that starts to look like a pretty resilient system because they've gamed the system in their favor to be able to have a regular cash flow. Okay, as a consumer, you might say that that's not fair, but it is a legitimate way to formulate that system. I'm just pointing out that maybe one of the things that has to first be done in figuring out if you have a resilient system is figuring out what your system is. How broadly are you willing to think? With that thought, I'll turn it back over to Ivan.
Our next question is from Chuck, and it is intended for Mark, although I believe Jennifer's presentation also touched on this theme. So, Mark, in the early shuttle days, we did the whole mission segment joint integrated sims, JIS. You remember them well, I'm sure. That's him saying, not me. The sims' job was to stress the whole system, including the crew, MOCR. You have to explain what that acronym means, science teams, etc. But we gave up because these were very expensive. The question is, can a cost-constrained program decide that it can afford to do these whole system JISs? Are they required?
So this is kind of like what I was asking Jen earlier. Do you need to hit the system and stress it in order to assess its resilience? In this case, some level of its performance. So we know we'll have to out this person because this has got to be Chuck Oman, who both Jen and I know, one of the people who taught us to think at MIT. And that goes back. MOCR is Mission Operations Control Room, so mission control. But I'll defer to Jen to see if she has anything to say about that first while I see if I can come up with an answer.
Yes, and if that would be Chuck, that would be lovely. I haven't seen you in forever. So I would say that again, when we look at the life cycle cost of a program or product, the cost to make changes downstream is hundreds of orders of magnitude more than it is to make them upfront. So where I think we can run aground is by spending the money to do this when it's very late in the flow and we're just now getting it into the sim. If we could find the ways to do this earlier on, which we don't typically do, we write a ton of requirements and then we go off and bend metal. And then when things look pretty near done, we do some tests. And if it doesn't work, we figure out how to train them differently, or maybe we'll pay for one or two changes, but otherwise we just live with it. Right. And that's why a lot of times we get the kind of band-aided systems that we're living with rather than having the opportunity to go back and actually correct or do differently. So the idea of more iteration earlier on, I think, is what could enable these sims to be done in a more concentrated way with more stress and with more systems engaged in it. That requires everyone to play ball from the beginning. And I know that we worked very hard to try to get mission operators and trainers to come in from early discussions on how we were going to build a system. And we would say, hey, how would you train this? And how would you operate this? And they're like, well, show me the system and then I'll tell you how I would train it. And I'm like, but that's too late. I need your expertise and knowledge now. So I agree it's way too expensive because I think they were doing it too late, way too much fidelity and way too much maturity. If we find ways to do this process earlier and more often in a more of a beta version, I think we're going to find a lot more bugs and be able to actually make more impact. So that's one thought. There are many others, I'm sure.
I
Yeah.
want to chime in one thing on this, which is when you continue to use it in a single mission framework, you don't see the end product itself as an iteration towards another next mission in the campaign, right? And so at the shuttle, right, if you use it enough, you get to the point where it's probably not worth stressing the system. If you're going to the moon and then to Mars, you have natural experiments where you are stressing versions of these systems. And you damn well better leverage that by censoring it up and capturing all that information so you can iterate it into the next system and figure out those ways too. Early, absolutely. But you are stressing the whole system, not as a sim. The moon is going to be a sim for Mars in some ways. So fine, treat it that way, capture the information, and make sure you've got the processes in place to feed it back in.
That's a fair point, but there is a limitation to that, which is in this particular case, I'm sure that Chuck is referring to Space Lab missions, which was Space Lab was a module in the back of the shuttle in the cargo bay. And I know Chuck was involved in several of them. I was involved with two of them when I was in graduate school. And those are a different crew, obviously, but a whole different complement of experiments. Highly integrated. Sometimes the crew was working on shifts, on off 12 hours. Very complicated logistically, a lot of fallbacks for equipment failures, and if something worked out really well, you'd want to try something different. So that doesn't, I mean, everything can transfer from one mission to another, generally speaking. But in those cases, that kind of training was very mission specific. So I mean, it's a rhetorical question. I'm not looking
No,
for a
I actually
comment or
think
an answer.
it's not rhetorical. And the reason
Okay.
why is because when
Yeah.
NASA's ACR came up and said, what are our tech gaps? One of the things that we've pointed out over and over again is, hey, you're not doing tons of science in space. You're collecting samples from humans and sending them down to the surface. You are doing some science in space, but a huge amount of it is not actionable based on the ways that we've constructed science in space. So if you can now update, you want to look for a place for autonomy, it is actually putting laboratory capabilities, scientific capabilities in place and starting to remove the humans from those so that you're not actually trying to do that intricate dance or ballet, but develop that capability. And I'll give you one quick example, which is when they use the MinION to swab the surfaces and say, hey, can we identify what is on the surfaces of these, parts of the ISS? That is a 6 months to a year turnaround on information that takes very specific scientific things, and then you freeze it and send it down to the Earth, right? When they did it with Spaceborne Computer 2, with edge computing and automated all of the analysis, they reduced that 6 month to a year turnaround to 11 seconds. So the things that we are learning, even from those how do you do science in space, should be feeding forward into doing it more autonomously and doing it better.
That's true. There are absolutely generalizable things that can, of course, then it begs a question. We could go on like this all day, right? It begs a question of, well, geez, you don't necessarily generalize things that are anomalous for that particular mission, quirks of a particular mission. It's like, why are we carrying this training load? Well, that's the way we did it 10 years ago, and nobody ever looked at, that happens in large systems. So it takes some planning and discretion, which all of this should. Okay, we have time for one more question. Actually, we are over time, but this group is magnanimous and has a lot to say. But we will hold it to it. So I apologize for the people who have submitted questions that we did not get to. If they're amenable to it, we can farm those questions around and give you written answers to them, or maybe we'll do a part two online sometime because this is a big topic and obviously has engendered a lot of interest. So I'll go to Ivan for our last question, and then I'll allow our three speakers to say anything in conclusion if they would like to. Ivan.
Okay, our last question will be from Stephanie. With resiliency being an integrated condition, how much do you see the design of the environment, specifically space habitats, impacting human resiliency? And I know Eric and Bill will have thoughts on this.
That's exactly Bill's thing, is how the environment impacts well-being.
Yeah, no, I think that it's a great opportunity from a design standpoint to create not just an environment, but a dynamic environment that's subject to reconfiguration, based again on changing conditions. With the monitoring in place, and I agree, I think, monitoring itself should be considered a countermeasure, as we got to figure out what exactly we're monitoring and how we're going to kind of define that. But from a performance standpoint, you can look at health and performance differently. I mean, obviously pathology, I agree, we should have some sense of what's normal adaptation versus pathology. And I think we could, I think we could do that. And then it would probably correlate to some degree with performance. So as we start to see performance degradation, you at least know something is wrong. And I think with iterative modeling and with kind of defined solution space, I think AI could help us identify what is the proper countermeasure, if you will, or the proper reconfiguration of the environment to, again, restore normal function. Jen had talked earlier about the importance of recovery. I meant to come back on that from a performance standpoint. It's not that you can't perform at very high levels for, periods of time, but it is allowing these periods of recovery that get built into that system. You can't do everything forever. So I think that can be built into that. But for sure, the ability to design an environment that is conducive to multi-system resilience it's a good opportunity.
So there is the idea out there, Bill. This is very timely since we just met someone, Stephanie Brick, who works salutogenic design, salutogenic architecture. You can build the environment so that it is conducive to, let's say, well-being, resilience, perhaps. Or you can ignore that aspect of things and, if not make things worse, at least miss an opportunity to help the crew.
Well, this is something that we've seen the beginnings of this at various points in the space program, right? The blue shifting and red shifting of lights on the ISS is a dynamic aspect of the built environment that is designed to help with circadian entrainment and sleep, right? We always have fights about, is there room for private crew quarters in any given environment that we have? And that's a big question mark in the volume trades in any habitat. And you better believe that having a little private space of your own is going to do a lot better than forcing you to like always be in the face of your compatriots, right? The Apollo astronauts were adamant about, please, for the love of God, don't put the kitchen next to the toilet, right? Smells, right? This is all about the built environment. So when I think of resilience, especially on the human side, the cognitive and the behavioral resilience, I think it's all about the built environment. And I think that salutogenic design is where things need to go next, because what we've done up to this point is get it to barely good enough, right? Get it to what will work for the shuttle, get it to what will work for the station, you know, where we have all these advantages of Earth. And even though the mass gets harder as you go farther away to Mars, so does the human question. And so how are we going to balance those? Because humans are going to take up more and more of that risk. Human failure was not a consideration in the PRA analysis for the space shuttle that only went up to 17 days in space. Human failure is a very real consideration in lunar and Mars missions as one of the reasons why we can't do our mission.
So again,
Oh,
define the system properly.
I'll add that you could argue that what you're talking about is design, right? And that is an entire discipline unto itself that tends to get thought of as a nice to have. As Eric said, it's basically what's the minimum that we need to survive. And anything that's seen as beyond that is, you know, too expensive and also gets traded off very easily. You know, the ISS wall that salmon was their attempt to be like, oh, now we're going to monitor, now we're going to contribute to your well-being by adding color theory to the space station, right? So they're the one little section that isn't blue or white, right? I think that people underestimate the design of environment, and also there's a set it and forget it idea too, where here's your system, this is what you've got. The ISS, you can see what happens when you start to live in it and you need to actually put things where they matter. And now it's completely untenable, right? So I think also designing for flexibility. We talked about resilience, but flexibility is another concept, right? That says, can I move my living room furniture around because I'm tired of it, right? Or this isn't actually working for me, or somebody else built my house, but I never lived in it. And so I need it to look differently now. So we need to also find ways to, again, from the outset, assume that these things are going to have to adapt and change. And that does impact absolutely our ability to perform.
Yeah, I thought that's on my list as one of the actionable ideas is don't make things, I mean, you want safety interlocks and things like that, right? You don't want to plug the nitrogen into the oxygen feed. But maybe someday will come a contingency when you need to do that. So don't design out capabilities to kind of break the rules, let's say, to do the unexpected. But don't make it easy necessarily, but allow for that. And that's an idea, the same idea as reconfiguring personal spaces and workspaces.
Yeah, and Mark, just real quick, you brought up another point. You know, a good friend of mine who's a former astronaut often said, not everything has to be fancy, right? Sometimes just give me the mechanical thing, because that I could actually fix with minimal tooling, right? If it's so fancy and updated and technologically, you know, supreme, right? Sometimes it's really hard to actually make the thing work when you need it to work. So I think two, we overcomplicate, right? And you could point to lots of differences in different countries' systems of the space flight and how we've over-designed, right? Over-designing is a thing. I mean, look, and I'm a recovering engineer, so I get it. But I think that again, it's something to carry forward too, that not everything has to be pristine, I'll say.
I agree completely. I am sitting in a room, if you can't tell, full of 60s and 70s electronics technology because I understand it and it's fixable. It was sophisticated for its time, but that means it's, compared to today's standards, relatively straightforward. So when something goes down, it's easy to do a workaround. It's easy to do a repair. It's easy. It's not so intertwined that you dare not open it up and try to poke around and fix it or get a workaround. Okay, I'm going to go around the figurative room, and yes, what Eric just put in the chat, I'm going to do. But let's go through in the order of the speakers and see if there are any wrap-up comments. Eric, you're not obligated, by the way.
No, I appreciate it. I just there was, there's a lot of questions that were in the chat that we weren't able to get to, and some folks have asked, are there ways to ask other questions? But the one thing that I would just say is, this is part of the reason why we started the Organization for Space Medicine, Engineering, and Design, was to have a place to have interdisciplinary conversations like this, and to try to make sure that we all have pathways to learn from each other. So I think if people are interested in continuing to have these types of discussions, go to osmed.org. Join, and let's continue to have them.
I agree. There was a question about whether it would be possible to keep in touch with the speakers after this symposium, and that is the answer to it. You can also email me directly, and I may or may not forward your question to the speakers. Depends how I feel that day, and depends on whether they want to hear the question and continue this. But so yes, mshellhammer@jhu.edu. You can find me online fairly easily. Any of us actually, but OSMED is the way to do that on a long-term systematic basis. We're all members, all four of us. Jen?
I'll just close with, somebody asked earlier, yeah, humans are varying and messy, and how do you actually do this, right? And what I will say is we do have ways to do this. We have ways that we can do it better. I pointed some out. But to me, the win is when somebody like yourself is sitting in a room and asks the question, are we thinking of this? Is anybody thinking about how we're going to design for flexibility and resilience and changing capacity? And are we stressing the system in all the ways that we can? So showing up in a room where you have influence and the ability to ask thoughtful questions that get people thinking in these directions, to me, is the first step, right? Because we want to be having these conversations in all the rooms with all the teams and bring this to the forefront of the conversation where it hasn't really been thought of this way before. So that, to me, is a great place to start.
Excellent. I agree completely. Yeah, this may take a cultural and generational change. So the time to start is now. And I have to say, the students that I'm getting are more, they might not understand what I mean when I'm babble on about multi-system resilience, but they are at least multidisciplinary thinkers. They want to think across boundaries, and that is a huge step in the right direction as well. Bill.
Just kind of echo what Jen said. I mean, I'm optimistic. There's the rate of technology change, the way AI is allowing kind of data integration and the modeling capabilities. I think what is now kind of conceptual models is we're trying to form just what resilience, multi-system resilience really is. We'll get kind of more formalized into mathematical models, formal methods that will then be able to serve as a foundation for technology platforms that will really allow us, from a monitoring standpoint and an intervention countermeasure standpoint, to keep humans operating at very high levels in very complex environments without breaking down.
Very good. There is something called resilience engineering. It's a discipline that's out there, right? I think I would say it's still a work in progress, but it's a version of some of the things that we were talking about. But that'll be our final technical point for today. So I'm going to wrap it up and thank all of our speakers tremendously for not only for being here, having great content, but staying a little bit over time. The Hopkins at Home people, Joe and Patrick in particular, Ivan, and everybody who's been involved with this over the years. This was a great experience. I hope the audience got as much out of it as I did. And we'll see you again online in a few months for our next symposium. Thank you.